Jeff Yarger. I'm a professor of chemistry, biochemistry, and physics at Arizona State University. I want to take some time to discuss the basic mathematics we use in looking at thermodynamics in biochemical, chemical, physical systems. And really this is meant to be just an overview of some of the math we do. Most textbooks that cover thermodynamics, both from a chemical perspective, in physics, and in biological systems, go through the general calculus needed to express thermodynamics. And this is really meant to be just some overview of some fundamental concepts that we use all the time when we look at thermodynamic systems. And the way I often say thermodynamics is more or less an exercise in, partial derivatives. And so I really want to kind of express what I mean by that. And starting back in the beginning, so really all we're going to be looking at is multivariable calculus from a very simplistic standpoint, from some of the basics of multivariable calculus, is all we really need to be able to use thermodynamics to its pretty much full potential when we're talking about equilibrium thermodynamics. So I like to start with, what are we talking about in partial derivatives? Well, let's just review what we mean by a derivative in general. And this is generally, you can define it very mathematically, and the limit as something changes, an infinitesimal change in a function as a function of a variable. I generally, and the reason I draw this as slope is, I generally think of it as we have some function and we're looking at the tangent line or the instantaneous slope, and that's, the first derivative. If we look at a second derivative, that's how the slope is changing. So it's curvature of some sort, etc. So I often think about this in pretty graphical terms. But this you'll find in any basic math book to go through. Now, really what we spend most of our time with in thermodynamics is more than one variable. Even some of the simplest thermodynamic systems, ideal gases, where you change pressure and you see how its interactions with volume and temperature, number of moles, etc., we're always looking in more of a multivariable space. And so when we use more than one variable, we move from a total derivative to partial derivatives. And we change it from a small d symbol indicating the derivative to a symbol shown here as a partial. This was introduced by Legendre back in 1786 was when this symbol was introduced, and Jacobian mathematics used it, is where it really became popular, etc. But really what this is meant to, it acts like a derivative of a single variable where all the others are held constant. So oftentimes you'll see this, and I've drawn it in blue here. The way you would read this is the partial derivative of f, with respect to x. What's implied, we oftentimes show explicitly, is that there's more than one variable, and all the other variables that are dependent or can change, they can have derivative properties, are held fixed. And we take the derivative with respect to each variable independently in the same manner we learned to take the derivative of a single variable function. So we take it with respect to each variable independently. So this one, for example, is basically implying that you're holding y constant, and that f is a function of two variables, x and y. And then I've shown just some common nomenclature down here that, this function that's a variable of x and y, that we can take the partial with respect to each variable independently. And sometimes instead of just using the function as a function of x and y, we'll often use some other variable. In this case, if we're using two variables, x and y, the most common thing is to use z or to use z as a variable. There are several other, and oftentimes in math, it's just this. It's several common nomenclatures that often can be confusing, because another one is that got popularized is to use a dot on top for a derivative, etc. So I'll always try to keep it common, but anytime you see this, it's pretty ubiquitously used now as a partial derivative. So when you have more than one variable, that also means that that the order of operation has to be considered here. So like we said earlier, if you look at with respect to one variable and we take not only the first derivative, but we take it, we take it with respect to x, but then we do it again, that's looking at how not only the slope of something, but how the slope is changing or its curvature, And so that's kind of what this gives. And this is looking at the other variable and what it does in its first order derivative, which is like the slope, tangent line or slope, and its second order derivative, how its curvature is changing or gradient. And then we have two terms which kind of say something about, is there an order of operation dependence? And in general, when we're looking at smooth continuous functions, etc., it doesn't really matter. It's path independent. In fact, this is one of the tenets we introduce in thermodynamics that has its foundation in the idea of it being an exact differential or exact derivatives. In that we say that all these energy functions that we've been talking about, internal energy, enthalpy, Gibbs free energy, Helmholtz free energy, etc., are state functions. And we say that a state function is defined by something that is path independent. And really what this comes from is the idea that these cross derivatives or mixed partials are, that basically these things, are equal, and that it doesn't matter if you go, if you do as a function of x first and then y, or you do y first and then x. And so we would express that, like we have here, that the mixed partials are equal to each other. So it doesn't matter which path you take. If you do if you look at the change in one first and then the other, or the other and then that one, you're going to end up in the same place if it is an exact differential or exact expression. So all state functions have the mathematical property that their total differentials are exact. So this is a very important point. So now we've looked at what partial, we see remember what derivatives are, kind of introduced that partials are the idea when you have multivariables, that we look at each one independently. And now we see that exact kind of says that it's independent of the path or the order in which you look at the operation of these variables. So I like to always put this, so in other words, if we're going from this point here to some other point, it doesn't matter if we go along x3 and then to here, that path, or we first do y and then x. We're still going to end up on the same point. So if this was, the internal energy, if this was the enthalpy, if this was the entropy of the system, the Gibbs free energy, etc., it's not dependent. The one I like to use often as an analogy here is the height of a system, which can depend on, x and y coordinates. In other words, if you pull out your altimeter and you're going from one point, say here, to some other over here, you're going to get the same change in height or the change in the altitude from one to the other, no matter what path you take. It doesn't even matter if you take some really crazy path, you're still going to end up at the same change in altitude or the altitude that you end up measuring from one place to the other. Now, some things are path dependent. The amount of work and heat you do getting there, the number of steps you have to take, how many calories you burn are very dependent on the path in which you take. But the altitude that you started at and ended at are independent of the path in which you take. And so, when you have that, that's when you can write these things in this type of nomenclature, which you will automatically see as the form which we see, thermodynamics in. So bringing it to, the internal energy, the energy that we first look at in thermodynamics, and we define as being work and heat. We can pick two variables and express that knowing that this is a state function. So knowing that it's going to have an exact differential, we can express it in two variables, two thermodynamic variables, and we need one variable for each one for heat and one for each work term we have. So this is implying that, something like a closed system, so there's no change in the number of moles. This would normally be dependent also, so we can define it with two variables, and in this case we'll do the volume and the temperature. And now, because it's an exact differential, we can write it as this. Oftentimes these partial derivatives are themselves a thermodynamic something we give a name to. It's such a common thing that we look at in thermodynamics that we give these partials. For example, the heat capacity at constant volume is defined to be how the internal energy changes as a function of temperature at constant volume, or this partial derivative. And then another important thing, which is, so once you know this, that we're dealing with things where the cross derivatives are equal, or there's no mixed partials, then we can use chain rules, cyclic rules, reciprocal rules to manipulate these partials around. And this is something that should inspire you to really make sure you go back and look at probably the most fundamental, like the chain rule in multivariable calculus, et cetera, because it's used so often in manipulating these to variables that are known in some type of problem. So with that, there's a couple consequences of that what we're looking at mainly in thermodynamics. Often what we want to know, these energies are state functions. And so they're exact partial derivatives, or differentiation. And so it leads to a couple things that we use all the time. The first is this idea of a Legendre transform. And what I'll say generally, which we all have a conception for, which is if we have something, so some, function f of x, so, it's drawn here in the xy plane, we can define this function as a function of x and y coordinates, right? But that's not the only way we can define it. It's just as equivalent to say, something about, for example, its radius and its angle with respect to it. Or in other words, we could put it in polar coordinates. We can put it oftentimes in two different variables that are more convenient for a problem to be solved. So we can put it in terms of, the slope and the intercept, which oftentimes we write as y is equal to mx plus b. So instead of knowing, y and x, we can instead know, the slope and the intercept. And from knowing this, since the slope and intercept, in other words, tangent lines at every xy coordinate point for some continuous function, that's equivalent. We know by having that information, we can also, map out the function as well, right? So the interesting thing about this and the Legendre transform is that these two variables are very specific in that the slope is related, so it has a relationship to the xy. And its relationship is that it is the derivative. It's the partial with respect to that variable, right? As we put here. In this term, they put a dot on top to indicate the derivative. And it does, we still get y coordinates. They're not the same. For example, at this point here, this is the y coordinate and this is the x. Here, we have a slope and we have where, it crosses the y here. So, but if we take a whole series of those by its derivative or tangential function and where it crosses the y-axis, that gives us a set of variables. We've changed the dependent variables from x and y to the derivative of y with respect to x and a y point where, in a sense, its intercept is along the y-axis of that tangential line. So that allows us to change, variables, right, based on a derivative property of the function itself. And so, for example, we say the internal energy, it's naturally dependent on the entropy, how the entropy changes, how the volume changes, how the number of moles change in a variable in every work term, right? So if we take a closed system, then it's, to keep it simple where it's just dependent on two variables, the entropy and the volume. So again, knowing that this is a state function, exact differential, we can write it in this terms here. Now this is how we write the combined first-second law. This is also true based on the fact that it's a state function and exact differential. And so, this gives us, the natural variables we're working in, which is it's naturally dependent on how the entropy changes and how the volume changes. So we can do a Legendre transform to, in a sense, transform which of these is the dependent and independent variables. We can do one Legendre transform like enthalpy, where we do a Legendre transform just on, this side. And so the way I always remember it is I remember this one equation, the combined first-second law for internal energy, and then I remember that enthalpy is a Legendre transform on PDV work. And I remember it kind of simply as you switch the variables and switch the sign. So we switch the independent and dependent variables, and we switch the sign from a minus to a plus. And now this is the fundamental equation for enthalpy. The Gibbs free energy is two Legendre transforms. The enthalpy one, the same one, right? So we could also write this as H minus Ts. And then one on this, where it changes this dependent independent variable too. So in a sense, we reverse both of these. We say it's minus SDT and plus VDP. And now the dependent variables are temperature and pressure instead of entropy and volume. And as I've stated before, often this is why we do these transformations, because these are dependent variables that we have more control over experimentally typically. The temperature, the pressure are things that we can imagine ways to control, to make constant. To make a constant pressure, to do it in an open atmosphere, to make things at a constant temperature where we have a constant heat source that's keeping something at a constant temperature. It's much harder to think of ways to keep the entropy constant. Volume you can keep constant often very easily in a computer simulation, but often not as easily or not as safely in an experimental lab. So this gives you some examples of a really important when using these the properties of these partial derivatives to look at this Legendre transform that we use to get to these different forms of energy that we often look at. Just like we could look at this problem as, instead of defining it by its xy points, its slope and intercept, now we have different energy terms we can look at that are dependent on different variables. So each one of these, like we said, is, now we have our Legendre transforms, which define, different types of energy for different problems. For example, when we have constant pressure, the change in enthalpy is often equal to the change in heat for a closed system. For the Gibbs free energy, if we keep things at constant temperature and pressure, then it'll be zero. And if you have an open system, though, or if you allow the number of moles of something internally to change, then you can look at just that chemical work term under those conditions, etc. Now, again, because the mixed partials, are equal, this allows us to, in a sense, define what we say are Maxwell relations, which are basically looking at the mixed partials, as shown here, between these different variables. So taking the temperature, which is the independent variable here, times its dependent, how it changes with this dependent variable at constant entropy, and then minus the pressure, how it goes into the entropy at constant volume. In other words, it's just looking at these crosses in each of these. And this defines a series of partial derivative substitutions that we often make for convenience sake, because of how we measure things. For example, looking at this one, you can imagine how the entropy changes as a function of pressure at constant temperature. It's hard to devise an experiment that might look at that. But looking at how the volume changes as a function of temperature, right? Or in other words, how something expands under constant pressure conditions, is something that seems more experimentally tractable. And because of this idea that they're exact differentials and state functions, we can make these substitutions to partials where we have more of an experimental handle on the variables, the dependent variables we're looking at. So I hope this gives you an introduction to using partial derivatives in thermodynamics and some of the power that comes from this. Thank you.